In this video, you are going to learn about convergence test of power series. Given we have an infinite series, where an infinite series is in this form, AR, where R start from 1 up to infinity. So when we expand this summation, we get A1 plus A2 plus A3 and so on, plus with AN and others. So this A1, A2, A3, A4 are called as the terms of the series, and this AN is the nth term. So the nth partial sum will be S sub n, where we can write it as AR, where R start from 1 up to n, because we only want to find the n sum. Okay, meaning that we will add all the terms up until an. So that's why the R would be from 1 up to n. So if we expand this summation, we will get A1 plus A2 plus A3 up until an. So this is called as the n partial sum. So if the sequence of this n partial sum is convergent and the limit of S of n, okay, where n approaching infinity is equals to S, meaning that the limit exists as a real number, then the series of the summation of AR, where R equals to 1 up to infinity, is also convergent, and the infinite series of AR of R equals to 1 up to infinity would be equals to S. So this value of S is called as the sum of series. Okay, but if the limit of S of n, where n approaching infinity, does not exist, it means that the series AR from R equals to 1 up to infinity is divergent. So here are the list of the convergence and divergence tests that will be used in this chapter in order to determine if the series converge or diverge. So the first one, you will learn about geometric series. Second one is ratio test, integral test, and the last one is divergence test. So let's observe this convergence test of power series. The first one is geometric series. The geometric series can be written as in this form, where it is the summation of AR to the power of n minus 1, where n start from 1 up to infinity. So A is the first term of the series, and R is the common ratio. So the geometric series is converged if the common ratio R is between 1 and negative 1. So since it is converged, then we can find the sum of the series, where it is equals to A over 1 minus R to determine the sum. So this is the formula in order to determine the sum of the geometric series. And the geometric series is diverged if the common ratio R is greater than equals to 1 or it is less than equals to 1. So let's try this example. Determine whether the series converge or diverge. And if it converge, give it sum. So here you can see the question where this series is the same form as the geometric series, where this form of geometric series is A times with R to the power of n minus 1, where n start with 1 up to infinity. So you can see here it is equivalent to this geometric series. So now we can determine the value of A and also determine the value of the common ratio, which is R. So based on this, we make a comparison. So you can see here our A would be equals to 1. Okay, because there is no value at front of this fraction. Okay, and for r, since r is to the power of n minus 1, so same goes with this one, so which means that our r value is equals to 1/3. So using the geometric series, okay, so if the geometric series, the value of the common ratio is between 1 and -1, it means that the series converge. Okay, now we can see that our r value is between 1 and also between -1. So which means that the series converge. Okay, so once we know that the series converge, we have to determine the sum of the series. So to find the sum of the series, we know that using the formula, which is a over 1 minus r, so a would be equals to 1 over 1 minus 1/3, 1 over 2/3, or can simplify it as 3 over 2. So this is the sum of the series. So the sum of the series is 3 over 2. Now let us try another example. Here we can see that the series is not in a general form. Okay, what can we do is that we can determine the value of the first term, where this one would be our first term, where a equals to 1. Okay, now we have to determine whether this series is a geometric series or not. So what we can do is we have to find the value of r, the common ratio. So to find the common ratio is that we have to divide the next term with the previous term. So it will be, let's check with this 2 first. So it will be -half divided by 1, which is equals to -half. So we have to check whether all of these differences using the same common ratio or not. So for the third and the second, it will be r equals to 1/4 over -1 over 2. So it would be the same, which is -half. Okay, and then you can see here, it's already give you the end. Okay, this is the end term, where this is in the form of -1 over 2 and -1. Okay, so there are two ways in order to determine the value of a and r. Using the first one is using the manual one, or we can just straight away use this n term, okay, to find the value of a and also value of r. So from here, you can also using the same method as the previous question, where this one is our a, the value would be equals to 1, and our r would be equals to -half. So now we have to determine whether this series is converged or not. So we have to check our value of r, whether it is between 1 or -1 and -1 or not. So our r is -half, where -half is between 1 and also -1, because this one is -0.5. So which means that since it is between 1 and -1, we can conclude that the series converge. So since it is converged, we have to determine the value of its sum. So S would be equals to a over 1 minus r, where a is equals to 1 over 1 minus -half, 1 over 3 over 2, which is equals to 2/3. So the sum of the series is equals to 2/3. Now let's observe the other convergence test of our series, which is ratio test. let summation of an from n equals to 1 up to infinity be an infinite series with positive terms, and we let this series with the limit of n approaching infinity of the absolute value of a of n plus 1 over a of n equals to rho. Then the series converge if we get the value of rho between 0 and 1. The series diverge if the value of rho is greater than 1 or rho is equals to infinity. And the test is inconclusive if you get the value of rho is equals to 1. So for ratio test, there are 3 answers for the test. First one is converge, second one is diverge, and the last one is inconclusive depending on the value of rho. Now I'm going to show you how to use the ratio test to determine the series of this 2 to the power of n over n, whether this series converge or diverge. So these are the formula for the ratio test. Okay, from this formula, you have to determine what is an and what is an plus 1. So an is just that obtained from the function from the question, where this refers to an, 2 to the power of n over n. And for an plus 1, okay, what is an plus 1? It's just that you just have to substitute n plus 1 into n. So here it will be 2 to the power of n plus 1 over n plus 1. Okay, now we have determined what is an and an plus 1. So now we can find our rho, where we just have to substitute all this into the formula. So I just rewrite back, where this one would be limit of n approaching infinity of absolute value of an plus 1 divided by a of n 2 to the power of n over n. So rearrange this since it involves divide, so it would be 2n plus 1 over n plus 1 times with n over 2 to the power of n. So now I just rewriting this back, 2n plus 1 over 2n times with n over n plus 1. So we know that for 2 to the power of n plus 1 is equivalent to 2 to the power of n times with 2 to the power of 1. So we can write it as 2n times with 2 to the power of 1 over 2 to the power of n times with n over n plus 1. Where this one we can cancel out, okay, and what is left is just limit of n approaching infinity of 2n over n plus 1. So for this case, you can see when you substitute n with infinity, you will get infinity over infinity. So remember, you have learned in improper integral, where if it's infinity over infinity, we can use, and it involves limit, you can use or you can apply L'Hopital's rule, where you have to differentiate the numerator and denominator. So since here use the variable of n, so it will be differentiate with respect to n. So you can get 2 over 1 as n approaching infinity. So now you get your value, which is equals to 2. So now you get your rho here is equals to 2. So based on the previous slide, okay, if rho is equals to 2, which means that it is greater than 1, this means that this limit is converge. Sorry, not converge. The limit is diverge. Now let's try another example. You can pause this video and try this out first. Okay, and then play the video and check your solution. Okay, here using the ratio test, what we need to do is we have to determine the an, where an is just 1 over n factorial. Okay, so an plus 1 would be 1 over, so substitute n plus 1 into n, it will be n plus 1 factorial. So finding the limit of an plus 1 over an to determine the value of rho, here would be 1 over n plus 1 factorial times with, not times yet, okay, first divide with an, so 1 over n factorial. So rearrange this, you get 1 over n plus 1 factorial times with n factorial. So just rewrite this up. Okay, so you know that the factorial means that n factorial, which means that it is equals to 1 times 2 times 3 times 4 times up until n. And for n plus 1 factorial, it means that 1 times 2 times 3 times 4 times with n plus 1. So that is what it meant by n factorial and n plus 1 factorial. So here, for n factorial over n plus 1 factorial, if we rewrite this, okay, into this division up until n, divide by 1 times 2 times 3 up until n and n plus 1, you can see that we can cancel this out, okay, up until n. So what is left is just 1 over n plus 1. Okay, so now we have solved this, so we just substitute n factorial over n plus 1 factorial with 1 over n plus 1, where n approaching infinity. So here, when you substitute infinity, where you get 1 over infinity, which is equals to 0. So your rho is equals to 0, which means that the series converge. Okay, now I'm going to show you the last example using the ratio test. Here we have our function is 3 to the power of n over n factorial. So now determine what is an, and an plus 1 is equals to this. So to find the limit, or using the ratio test, it will be where this would be equals to so here I simplify this, or I will rewrite this 3n plus 1 as 3 to the power of n times with 3 divided by 3 to the power of n times with n factorial over n plus 1 factorial. So the method is just the same for the factorial from the previous question. Okay, where at the end you will get 3 over n plus 1, where n is approaching infinity. So 3 over infinity still you get equals to 0. So since it is equals to 0, which means that the series converge. Now you can try out this question by yourself, and the answer you should get the series converge and the value of rho is equals to 0. Okay, now we move to the next test, which is integral test. Let's say we have a function of fx, where this function is a continuous meaning that there is no discontinuity in the interval. Okay, and it is positive and decreasing function on interval 1 up to infinity. And we let this an as equals to f of n for n equals to 1, 2, 3 up to infinity. Then the series of the summation of an as n equals to 1 up to infinity is converged if and only if the improper integral of the integration of fx from 1 to infinity with respect to x converge. Okay, in other words, okay, we can simplify. If the integration of fx dx from 1 to infinity converge, then the series converge. But if the integration of fx dx from 1 to infinity diverge, then the series is also diverge. This is for the integral test. Okay, now let's determine if the following series ln n over n from n equals to 1 up to infinity converge or diverge using integral test. Okay, so we can see here the function that associated with the series, okay, is f of x equals to ln x over x. Okay, it's no longer ln n over n because we change this n into x, but the function is just remain the same, but we just represent this function in terms of x, where this function is continuous. Okay, you can see it is continuous. Okay, between this interval there is no discontinuity. Okay, and it is positive for x greater than 1. Okay, you can see x greater than 1, it is positive. Okay, and also you can see here as the interval from 1 up to infinity, the function is decreasing. So you can see if we make the interval larger, you can see the graph is approaching to 0, which means that it is decreasing. So now we can apply the integral test to solve this, to determine that the series is converged or not. So the function that is associated with this series is f of x equals to ln x over x. So now using the integral test, we know that f of x dx from 1 to infinity would be equals to the integration of this function, okay, ln x over x dx. Okay, now you can see this integration. This is an improper integral because why is this? This is improper because you can see one of the interval is infinite. So you have to use limit in order to solve this improper integral. So it would be limit of the integration of ln x over x dx. So the interval from 1 up to t, where t is approaching infinity. So solving this ln x over x first. Okay. So now what you can do is you can dx, where you can represent your u. Okay, we can solve this using integration by substitution. Okay, so we let u as ln x, and you can see when we differentiate this, you will get 1 over x dx. So this part here, dx over x, can be represented as du. Okay, and also our ln x would be equals to u. So solving this, would be equals to the integration of u du, where it becomes u square over 2. Okay, now your u is equals to ln x square over 2 plus c. So we have solved this integration, so we can just simply substitute into this limit, where ln x over x, the integration of this, is equals to ln x square over 2. You don't have to write the plus c. Okay, so this one would be 1 up to t. So now we can substitute this, where it would be ln t square over 2 minus with ln 1 square over 2. So you can see here for ln where t is infinity, which means that it would be infinity. Okay, minus with ln 1 which is equals to 0. So your answer would be equals to infinity. So since the integration of fx dx here is equals to infinity, this means that the series diverge. Now let's try the next example. Using the integral test, determine if the following series converge or diverge. So here we have to find the function where we can represent our function of x, which is equals to 1 over x squared plus 1. So using the integral functions, where the limit is from 1 up to infinity. So here would be 1 over x squared plus 1 of dx from 1 to infinity. So remember that you have to represent this integration as the improper integral. So you have to change to limit of 1 over x squared plus 1 dx from 1 up to t, where t is approaching infinity. So solving 1 over x squared plus 1, you will get inverse tangent of x. So here would be this minus with tangent inverse of 1. So tangent inverse of infinity would be equals to pi over 2 minus with inverse tangent of 1 is equals to pi over 4. So your final answer would be pi over 4. So since we got a value, okay, pi over 4, it means that the series converge. you can try out this example, okay, using the integral test and determine if the series converge or diverge. So here is the answer. Okay, now we move to the last test, which is divergence test. The infinite series of an as n equals to 1 to infinity diverge if limit of an as n approaching infinity is not equals to 0, or the limit of an as n approaching infinity does not exist. So this can prove that a series diverge, but we cannot prove that a series converge. By using the divergence test, determine whether the following series diverge or converge. So you can see here, using the divergence test, what you need to do is you have to find the limit of the function, which is n cubed, where n is approaching infinity. So you can see when we substitute n with infinity, the answer will be infinity. So since the limit does not exist, so the series diverge. Okay, now moving to the next example using the divergence test. So we have to find the limit of n over 2n plus 1 and approaching infinity. So substituting n with infinity, you will get this in terms of infinity over infinity. So we can apply L'Hopital's rule to get this, where it will be 1 over 2 as n approaching infinity. So your answer would be 1 over 2, where you can see that 1 over 2 is not equals to 0. So since it is not equals to 0, the series diverge. So for the last question, okay, the summation of negative 1 of to the power of n plus 2. So using divergence test, it will be limit of negative 1 to the power of n plus 2 as n approaching infinity. So if you see that when we try to plot this, okay, negative 1 to the power of 3, it would be negative 1, okay, and when it is to the power of even, you will get 1. Okay, you can see here it is negative 1 and you can see here is 1. So you can see it is alternating from negative 1 to 1 to negative 1 to 1 and so on. So there is no convergence into this value. So we can say that this limit of negative 1 to the power of n plus 2 as n approaching infinity does not exist. So since it is not exist, which means that the series diverge. So now you can try out this question, okay, and determine if the series diverge or converge.